Is that electromagnetic suspension?
Yes it is, you bet. I was going 80 miles per hour and guess what? We just stopped the car and there was no lurching forward.
No.
Hi, my name is Giselle and welcome to Cars with Giselle. I'm exotic Italian actress Giselle Caprizio-Capdevilla. You may be thinking, this girl looks familiar, and that's because I'm a film extra in a lot of movies. If they ever need a hot girl in a bikini in a movie, that's where I come in. I'm also one of the people that poses with the suitcase in Deal or No Deal. So that's me. Welcome to my show, Cars with Giselle. So, you may be thinking, those are silly jobs. And to that I say, I drive a Ferrari, and you don't. Good. So you may be wondering, why did I bring up my Ferrari? And also, why am I on the ground? Well, you're about to find out the answers to these questions in this episode of Cars with Giselle, where we're going to talk about electromagnetic suspension and, in general, electromagnetic applications in the automobile industry. So, see you back at the lab. Alright, so those of you who have probably heard about car shocks or car suspension, and what that is just a way to absorb the shock in your car. So basically, you know, your car is made of a stiff frame, right? So whenever you're driving and you hit like a pothole or a brake, then it really starts to kind of take a toll on your car. So that's what your car shocks are for, is that they absorb the shock whenever you hit, you hit your brakes or you hit a pothole. So what is what are car shocks? Well, basically, it's just a spring. And for those of you that have probably taken Physics 1, you know that a spring oscillates. So the difference between a spring that you play with in Physics 1 and the spring that is your car shocks is that it has a piston. And this piston has small holes in it that releases a fluid into your spring. So this fluid literally dampens the oscillation. So, whenever you hit a bump, you're not just bouncing up and down all the time. So, many cars have a sports mode, and the difference between a sports mode and, I don't know, like if your car doesn't, just a normal car, is that a sports mode has bigger valves inside of the piston that releases more fluid that increases the reaction time. So, there you go, there's the difference. So what is a magnet exactly? Well, I don't know, but luckily we have struggling physics student Anna Morales over here to help us out.
No, I'm not gonna do a video.
Oh, come on. Here, read this, okay? All right, we're good? Okay.
Hey guys, I'm Anna Morales. I'm a struggling physics student, and I'm here to talk about magnets. Okay, so what is a magnet? How does it work? Well, a magnet is a piece of iron that has its component atoms so ordered that the material exhibits properties of magnetism. Well, what is magnetism? We learned this in physics. Oh, magnetism is a force that moving charges exert on one another. What else? Oh, magnets have a magnetic force. What is a magnetic force? Well, an attraction or repulsion that arises between charged particles. Yeah. Hello you guys, it's Anna Morales, struggling physics student. Back at it again with the magnets. Here we have a whole bunch of equations. This one is the magnetic field or current of a wire, which stands this is a constant, mu, which is 4 pi and 10 to the -7. I is the current, 2 pi r, where r is the radius, and the whole units for this. Here we have magnetic force, Fe, which equals q times v, where q is the charge of the particle, e is velocity, times v, where v is magnetic. Here we have Fb, which is magnetic force, equals Q, which is the charge of the particle, times V times V,
about all these equations. Right here, you can see if you want to solve for the magnetic field, you use this equation right here. I'm not going to talk about this equation because this is the exact same equation that Anna talked about earlier. She just solved for the magnetic field algebraically. So moving on, we're in a different situation where there are two wires with current going through them. So if you want to find the force between these two wires with the current running through them, you would use this equation right here. So if you can't see it, it's equal to the current times the cross product of the length of the vector times the magnetic field. So you can use this relationship to deduce that, you know, if you have two parallel wires and the current is running in the same direction, they attract each other. But if you have two parallel wires and the current is running in the opposite direction, then they repel each other. So moving on, here's another situation where if you would like to solve for the magnetic dipole moment, that's equal to N times I times A, where N is the number of turns in the coil, I is the current running through the coil, and then A is the area of the coil. So you might be wondering, how do I solve for the area? Well, if you think of each coil like a circle, then just use pi r squared. So that's how you solve for the magnetic dipole moment when there's a bunch of coils in the wire. Moving on, here's how you find the torque. You take the cross product of the magnetic dipole moment and the magnetic field, which is your B. So there's that. Nothing crazy you've ever heard before. It's just, you know, what you do if there is a dipole. So last equation I'm going to talk about is the energy of a magnetic dipole based on its orientation in the magnetic field. So if I were to find that, I would take the dot product of what we found earlier, which is the magnetic dipole moment and the magnetic field. So there's that. Just know that, you know, based on its orientation, the energy changes. So there's that. Also, I would like to remind you guys that units are important. So just know that mu, the unit for that, is a joule per unit Tesla. All right. So you might be wondering, who cares? Well, if you guys didn't take anything away from this, because it is a bunch of equations, just know that I will be talking about the magnetic field, which is this equation right here, and I will be talking about the magnetic force, which is this equation right here. Also, I will be talking about this magnetic field equation. Okay, so you're probably wondering, what's the part where I talk about electromagnetics? Well, I'm about to get to that. So this word right here says magnetorheological suspension, and it's really big, but you can just call it Magneride. So basically what that is, as I explained earlier, whenever you have your suspension, you have a spring and then you have the fluid that goes into the spring that literally dampens the oscillation, right? Well, whenever you have Magneride, there are tiny iron particles that are suspended in the fluid that dampens the oscillation. So these are little iron particles. It's like 20 to 40% iron particles. So whenever there's no energy in these iron particles, they're just kind of like randomly oriented. So there's like a little solution inside the fluid that keeps it randomly oriented, so it's not getting all out of whack. But whenever it's gaining energy, you know, whenever you step on your brakes, therefore they gain energy. Well, then the particles align into fibrous structures that they form a structure that's perpendicular to your magnetic field. A good thing about this suspension is that it is fairly, it doesn't react whenever, you know, there's a change in temperature. So whenever it's hot or it's cold outside, you know, doesn't react very differently. So it's great. All right, guys, thanks for listening. Now you guys know about Magneride. But I should let you guys know before I turn you over that don't get all excited about Magneride yet because it's not in production. So you can't just go to your local Honda dealership and start looking for it because the cost of production is too high. So let's all keep our fingers crossed that we can all afford a smooth ride like me and that they're going to start incorporating it in all the dealerships. So now I'm going to go ahead and turn you over to Stephanie Lopez so that she can continue talking about the electromagnetic applications in the car industry.
Ever wonder how windshield wipers work? Okay, so before 1968, windshield wiper motors used to come with electromagnets, which we know from class, they need current to create magnetism. But after these groovy times, we started to make the motors with permanent magnets. As you can see in this rough sketch, are outside in the cylindrical motor. You wonder why we changed this? Okay, so before 1968, magnets used to be pretty crappy. They used to lose their magnetism pretty easily. But afterwards, magnets used to contain their magnetism up to 10 to 15 years, and that's why we made the change. Inside the windshield motor, there's a worm gear that multiplies the torque of the motor by about 50 times, while slowing the output speed of the electric motor by 50 times as well. The output of the gear reduction operates a linkage that moves the wipers back and forth. Ain't that interesting? Now for an interesting fact. If you want to change the direction of your windshield wipers, you could do this by changing the polarity of your windshield wiper motor, meaning that you switch the north and south magnetic poles. But you can only do this if your windshield motor uses an electromagnetic, which we know is really old.